Hello. In this video, we are going to look at a classic random variable problem. The learning outcome for this video is thus just to learn to be able to solve this particular problem, which involves calculating the probability that event X happens before event Y if both these events occur at random times. There are an enormous number of ways that this question can be asked, as you can essentially use different random events in the setup of the question. In the past, I have used radioactive decays, chemical reaction, drugs in the human body, getting to the gate in the airport, and so on. Point is that whatever the contrived backstory is in the question, the solution to the problem is always the same. I would thus think about the various ways that this question could be constructed in the exam in order to make sure I fully understand the general argument. Regardless, let's look at the particular instance of this problem that we are considering in this video. The question in this case runs as follows. Bob is waiting to catch a bus. Alice, meanwhile, is visiting the library before going to catch the bus from the same stop as Bob. What is the probability that Alice will meet Bob at the bus stop if we are allowed to assume that the time she spends in the library, capital T, is an exponentially distributed random variable with parameter A? The time Bob will have to wait for the bus, capital Y, is also an exponentially distributed random variable. Y has parameter B. I think this question is rather unimaginative, as it doesn't say what happens to Bob and Alice after they meet at the bus stop. I like to think that they fall madly in love, get married, have children, and finally die within a few days of each other after an extremely happy life. If you want to come up with a different story for Alice and Bob, you can do. The important thing, though, is that for Alice to meet Bob at the bus stop, she must arrive before the bus departs. If the bus arrives before Alice, then Bob and Alice never meet and their life of domestic bliss disappears. The question provides us with some random variables that we can use to model this business of Alice and Bob and the bus stop. We are told that Alice arrives after an amount of time given by a random variable called t. Furthermore, we are told that the bus arrives after an amount of time given by a random variable called capital Y. As the figures make clear, if t is less than y, then Alice meets Bob at the bus stop. If, by contrast, y is less than t, they do not meet. Hence, after all this palaver, we find that the question is just asking us to calculate the probability that the random variable capital T is less than the random variable capital Y. This is what these questions are always asking. It may be dressed in different ways, but underlying the quite often contrived description in the question lurks this business of calculating the probability that one random variable is less than the other. Before I show you how to calculate this particular probability, let's first briefly review the exponentially distributed random variable. We need to do this as if you look at the question, you see that t and y are both exponentially distributed random variables. If you remember, we saw that an exponentially distributed random variable is a continuous time Markov chain that can be used to model the process of waiting for an event to occur. The transition graph for this chain has two states as shown in this diagram. The first of these states corresponds to the event not having happened, and the second of these states corresponds to the event having happened. Furthermore, the first of these two states is transient, while the second is recurrent, as the event is guaranteed to occur at some point in the future. We can find a solution for the probability that the event has not occurred by time t by using the Kolmogorov equation. In a previous video, we saw that the jump rate matrix Q was in this case equal to the matrix shown here. When this matrix is multiplied by the matrix of probabilities, and when the resulting differential equation is solved, we found that P00, of t, the probability that the event does not happen during the first t seconds, is equal to e to the minus lambda t. Let's now return to the question in hand, the business of Alice, Bob and the bus stop. We cannot use the result we have just revised immediately, as calculating p, the probability that capital T is less than capital Y, is not simply a matter of inserting some particular t value into e to the minus lambda t. The problem is that t, Alice's arrival time, is itself random. We are saved, however, by remembering the partition theorem, which we learnt about in an earlier video. The point is that the set of all possible t values forms a partition of the sample space. We can thus calculate the probability that capital T is less than capital Y by calculating the sum, in inverted commas, of the probability that t is equal to a particular value, small t, and that y is less than small t. The inverted commas are necessary here, as strictly speaking we cannot calculate it as a sum, as we are dealing with continuous random variables. We thus have to calculate an integral instead, as shown here. Notice that the integrand here is precisely the quantity that I stated we needed to sum. This is the probability that capital T equals small t, and capital Y is greater than small t. The only thing is that I have written this out in terms of the product of a conditional probability and an absolute probability. In other words, I have taken advantage of the definition of conditional probability. The next important thing to note is that the question gives us no reason to believe that the random variables capital T and capital Y are correlated. Alice's movements will not affect those of the bus after all. This ensures that we can thus rewrite the conditional probability in the integral as an absolute probability. This is rather useful realization, as we now find ourselves in a position where we know all the required probabilities. The probability that capital Y is greater than t, for example, is the probability that the event does not occur before time t. We have seen that we can work out this quantity using the Kolmogorov forward equation. This probability is thus just e to the minus a of t. As if you look at the question, you see that it tells us that the parameter for the exponentially distributed random variable that describes Alice's arrival time is a. Working out the probability that capital T is equal to small t is slightly more involved. We need here the probability density function for the random variable capital T, which, if you remember, is equal to the derivative of the cumulative probability distribution function with respect to, in this case, t. Now, remember that the cumulative distribution function tells us the probability that big T is less than or equal to small t. Obviously, we can work out this function by taking 1 minus the probability that big T is greater than t. The probability that big T is greater than t is just e to the minus b of t, however, as the question tells us that the bus's arrival time is given by an exponentially distributed random variable with parameter b. We can thus calculate the required probability density by differentiating 1 minus e to the minus b of t with respect to t. This is a rather straightforward piece of differentiation. The derivative, in this case, is equal to b e to the minus b of t. We can now insert all the probabilities that we know into the integral. Pleasingly, we find that the resulting definite integral is a rather straightforward one. We begin by exploiting the rules of the exponential and simplifying the integrand to a single exponential function rather than a product of exponentials. We then take the constant factor outside the integral. We can now integrate to get the function shown in brackets. When the upper limit of plus infinity is inserted into this function, we get 0, as e to the minus infinity is 0. E to the 0 is equal to 1 by contrast, so the lower limit gives b over a plus b, which is the answer to the problem. In this way, we thus conclude the problem. As I have stated throughout this video, this problem can be asked in a wide variety of different ways, as different random events can be used for x and y. We use the arrival of Alice and the bus for the events x and y in this question. To ensure you understand the problem, I would not recommend solving the same problem 20 times with different scenarios. Instead, see if you can devise a question with this structure and this answer. Think of two random events that happen at random times and set an exam question that asks for the probability that one occurs before the other. If you can set a question on this stuff, then you will certainly be able to do the question that comes up. Thank you for your attention.